understand the jet. And then there are all the models which address very detailed, complicated physics, hydrodynamics, magnetic field, and so on in the jet. So I don't know, but one thing which, what is, according to you, if someone has an idea, what is the best way of joining these two things? Because we said that with Colibri, we'll have a lot of interesting data and so on. But how can we, what is the most efficient way to constrain the model, the physics, from the observation? It is something which leaves me a bit perplexed, because there is so, the gap is so big between these very detailed models and the observations that I have the feeling that we have a long way, but I don't know what is the best way to go to fill this gap. If someone has an idea, I would be very interested. And then we can continue this discussion if you have other questions.
Jean-Luc, can I complement your comment? Because I completely agree with you, because I have exactly the same feeling. And at our level, the question is very simple. Which kind of data we need to test all these models? What we need to observe technically to test this model? Otherwise, it would be almost impossible to discriminate them. It's a very practical question.
Yeah, can I comment? So with respect to the afterglow, the database which Damian was presenting will be great. So if as theoreticians we can get easily spectra, multi-wavelength spectra of the afterglow and the light cubes and so on, we can try to fit those light cubes with different models, with different structures and so on. No? So that will be relatively easy. And actually it's already done by a lot of people around the world. No? With respect to the prompt emission, it's a little bit more difficult because really we don't have a full understanding of the theoretical part. No? That's all.
But even if we start and we have all the data in the world, I think that some parameters are depending on each others, and I think that is very hard, but maybe even with the best telescope, we have some theoretical or natural complication to find or to solve completely all the JRBs. For example, like Jean-Luc mentioned before, the magnetization parameter and all the microphysical variables, I think that depending on each other, then could be maybe not just a technical problem, it's a physical problem.
Yeah, that's true that we have a lot of degeneracy. So unless we get GRBs with different frequencies and we can recognize the characteristic frequencies in the spectrum, so we can infer better the parameters. I mean, just getting a light curve at one frequency, really, you can say a lot about the theoretical model. You can't really say nearly anything, no? Substantial. So we need multi-wavelength observations. That's why I was asking to Damian if the radio emission was included also, and he said yes. So yeah, I agree with Rosa. We have a huge degeneracy. Also, when we have all the multi-wavelength observations, if we are in fast cooling, slow cooling, we have just two characteristic frequencies, or maybe three if there is a self-absorption frequencies. So we can get just a few parameters, not a lot of them.
Fabio, just to be clear, when you speak about multi-wavelength observation, what do you mean? from X-ray or gamma ray to radio, or
Yeah, from radio to gamma rays, and hoping that for instance, the 1708, 17A, there were observations going from radio to X-rays, but they were all in the same energy range, no? So they were in the same spectrum range, so all going as a nu to the minus p minus 1/2, no? So really, you have a lot of data, but you can't get a lot of information from it. So you need to have multi-wavelength observations, plus you need to observe the characteristic frequencies, hoping that the characteristic frequencies fall in this range. And ideally, you should follow the characteristic frequencies at a lot of different times, so that you can make a good afterglow model. Because in the afterglow, really, we know that it's mainly synchrotron, so we can infer the dynamics and the structure of the jet directly from the observations. In the prompt emission is much more complicated, no? Because it's not really clear the role played by synchrotrons, photospheric emission, and so on. So the theoretical part is not clear.
If I may, Fabio, so yes, you are talking a lot about the light curves and what you see from the jet, but also, I mean, for example, as you said in 1708, 17, you also have information of the galaxy, the region around the galaxy, etc. And if you were to have that for a collapsar, so a nearby collapsar, where you could also get very well pinned down what region it's coming, so what kind of progenitors you have, what kind of medium you have around those progenitors, all of that could also give you lots of extra information that you cannot get just from a light curve.
Yeah, that's true.
So a nearby collapsar would be amazing in that sense, especially if you can also get neutrinos and whatnot, right? So that could also give you a lot of, I mean, we don't even know how to make these stars pop in a different way than the usual supernova. You know, it's a massive star, but how is it getting this extra oomph, right? So that can be obtained simply by knowing where this thing popped and what kind of medium you had around.
Yeah, it depends on what you want to study. No, I was thinking just to the dynamics of the jet and the afterglow emission. But yeah, if you want to study the central engine and the progenitor stars, yes, studying the environment gives you good information about that. I agree. Also, there are the supernovae associated.
Yeah, Fabio, with your hand, please.
Oh, sorry. I was just mentioning that there are also the supernovae associated. That's all.
Damien Dornick raised his hand.
Yeah, for the theoretician, for what I understood, most of the modelization we know right now come from few GRBs, who very well sampled. I think it's less than 10 GRBs, and every modelization has been done only with this. We have thousands of gamma ray bursts, or even more, but at the end, everything is done only on less than 10. When you see all the likers, the modelization, the flare and everything, all the detailed model are done with very, very few gamma ray bursts. So is it not the strategy to not have a lot of gamma ray burst studies, but only few, but with everything is possible, all the data possible, follow using long-term follow-up with the multi-wavelengths and everything? I don't see really anything except the population coming from the huge amount of bursts we have. And them, I think, will not improve the statistic by a huge number.
And this is already, Damien, if I can have a comment on this, this is already something we have some implicit choice we have done when we have decided to select gamma ray burst in the night hemisphere at the expense of losing half of the swarm time by looking at the Earth. So we have already implicitly made this constatation that we prefer gamma ray bursts with a lot of information than many gamma ray bursts with little information.
Yeah, I completely agree with you. But most of the time, the people are asking how many gamma ray bursts will SOM detect, what is the statistic and stuff like this. But at the end, the statistic almost don't care. If we have 2 gamma ray bursts per year, but with all the data possible, I think you will increase your knowledge of the gamma ray burst physics.
One at 100 megaparsec and the other at redshift 15, the 2 gamma ray bursts.
Exactly.
Any other comment about this question? And if no, we can get to another question, but let's give a chance to everyone to speak.
Yeah, let me just add something to that. I think we learn a lot more from GRBs in general when we have extensive data sets. And so, you know, ideally we'd have, you know, multi-wavelengths, and we'd have redshifts, and we'd have light curves from the early part until the late part. You know, you can learn a lot if you see a jet break at 50 days. And with RAD-TIA, we've tended to do that. We've tended to observe GRBs as long as we can until they drop below our instrument sensitivity. And I think with Colibri, we have to do that. We have to be prepared to put in nights and nights and nights of observations to get great light curves at early times and at late times. And, you know, we have to put in as much spectroscopic time as well to get redshifts. And, you know, I don't know what the X-ray follow-up strategy is with MXT, but again, getting the X-ray light curve to complement the optical light curve is very important even at late times. So I think we just have to burn telescope time to get what we can.
I agree with you, Alan. Colibri has been tuned for that, so okay, we'll have to spend the time that we need.
Maybe before no, okay. Maybe before finishing, we can address another question. We can spend maybe 15 minutes on another question. If someone has another point he would be interested to discuss here, please feel free.
I have one, but to Damien.
Yeah.
Okay. It's on the base, on your GRB base. Clearly, it's an enormous amount of work if I can stop playing. What do you think for the future? How do you think this base will evolve and stuff like this? Because we have seen there were several. Khan has done a work, but he has stopped and everything. And this is really important for doing constraint and everything on the physics. So how do you see it will evolve in the future? And can this be a much global effort than you?
I can't hear you. You're muted. So you mean how?
Comment ça va évoluer? Comment tu vois évoluer? C'est un très gros boulot. Il y a beaucoup de trucs, mais comment ça va évoluer dans l'avenir? Qu'est-ce que tu vas mettre dedans?
Jean-Luc,
tu vas avoir plus de bursts, moins de bursts.
Yes, of course we will have more bursts. We will continue to fill this database as long as we have new bursts to come into the GCN or publication or so on.
L'interface avec After Bottom.
Yes, yes, of course. As I said in GRBase, we will have a huge database of data that we will continue to fill even during the SWAM era. Even from we will continue to fill Swift data, Fermi as long as they are alive. And what we want to do also, as I said, is to provide tools to make analysis. So, and especially for after models, for example, we have a couple of set of analytical models that are able to simulate or to model different structure of the jet. So you will be able, for example, to compare these different models. Those are analytical models, so well, we can only do these kind of things, of course. As long as we have new analytical models, I mean, it's a service we offer to the GRB community. So, well, Alain and Bruce could correct me, but if Bruce is still alive. But the idea is that we propose a service to the GRB community, so you have the right to use the data and the tools we are going to implement. But we would like also that, okay, you are going to use things, but we are also open to the collaborative effort to improve things. So improve tools or improve the data that are inside GRBase. So for example, we have only access to public data. If, well, we can discuss the policy afterwards, but if someone wants to, for example, to provide all data to GRBase because they were private, they were not have time to exploit them, we are very open to include those new data into the system. We can discuss how we can keep this private for people who are connected to GRBase and participating to feed with private data and so on, but this is, I mean, this is not now. And also if people have ideas to implement new models, new analytical models or new methods or things like that, or new plugins into the system, we will be open to any collaborative efforts. I mean, it's a service to the community, but I mean, just not consume the service, you can also improve it. I think it's one of the part I think it's important is that people can improve the system and it benefits to everybody afterwards. Currently, we are building, I mean, a basis of set of tools, but we are not sure, I mean, we are not gods, so we are not sure that it's going to fulfill all the requirements or your needs. And if you have some ideas, we can also help you to integrate your tools privately or publicly to the system, etc., etc. I think it's one of the evolution of the system. First, we propose something and then people make it evolve.
I think if I can add a comment, I think that what is very important is that to have an overview of what exists in the community and then to provide interfaces. So yes. What you have is quite unique, but then you have to provide the right interfaces yes. for maybe as after GrowPy or for other people or for this Jansky thing, for instance, is very important. So you have all the same units for everybody, or you can draw. I mean, yes, yes. It is very important to understand what is the global panorama in order for your contribution and your tool, which is this database, to be used by most of people and to be yes, developed and so on.
Things have to be very standard, so we have a lot of work to do to make the things standard. Like if you want light curves in millijansky or light curve in magnitudes or something like that, it will be, I mean, not so hard to make it. I think we will create a web interface, I mean, so that people could connect onto a website and they could use the functionalities of GRBase. So both, they could extract just the data as they want using some filters. I want GRBase with reverse shock, I want GRBase with plateau, I want GRBase with jet brake or things like that. So this is just data extraction. And then on this web interface, this is how I think it could be, but on this web interface, then you could use also functionalities like SED fitting, I don't know, light curve fittings or things like that, or you could just use some analytical models. So you have after GrowPy, as you said. David Core has implemented the model of Granot and Sari 2002 in a Python package, so this is also included in the GRBase package. We are working on integrating more and more analytical models that could be used by the community. So, but then, if you have a new models, or if you want to contribute to create, I don't know, everything will be probably in Python. So, if you want to contribute, I think But I mean, it's open.
Okay.
It's not closed. And it will be a web interface, I think, based. And the work Bruce is doing on LIA-ERIDANUS is going to help us also, because we will probably use some of the frameworks of LIA to the interface of LIA to transfer things to have a web interface for GR-based. But it's a lot of work, so just wait a bit. We are working on it, but I hope we will be able to propose a beta version or first version, at least for data extraction. Maybe not the functionalities like SED fittings, or maybe you could just plot some SED and just download the data. I mean, I think maybe in 1 year, Bruce or I could help me to answer, but it would be possible. Hopefully.
Okay. Thank you. So Bruce just told me that his birthday started only 2 minutes ago, because it's midnight now.
Yes.
It's midnight now in Australia, and so this is the day of his birthday now.
The response to the GRB.
Not technically only that, I'm born at midnight 04.
Alan, did you want? You said you could not raise your hand. Your computer does not allow that. Do you want to say something? I don't see you, but.
No, it's not there. No.
Okay. So, anybody else has question about GR-based or another topic?
No,
If I can just add something.
Oh yeah, sure.
Because we were only speaking about GRB community, but
yeah.
I hope that GR-based could be used also for multi-messenger astrophysics community based, of course, linked to Cabaradus. So we already worked with Damien with Antares data and trying to probe the origin of some high energy neutrinos connected to some GR-based, and we use some data from GR-based for this. So we have to think also to make some evolution, maybe some tools or some functionalities dedicated to multi-messenger.
Okay.
But I mean, this is, you can think about it. Then, for example, if you have some needs. I know you have some.
Rosa, you raise your hand.
Yes, maybe it's a very stupid question, but it's because I have no idea about neutrinos, but how you can put the observation of the neutrinos, or how you compare a multi-messenger astronomy of, for example, for the specific case of GRBs with neutrinos, what we can obtain for that with the neutrinos information, what we improve.
I think if you have hadron in a jet, the constraint on the baryonic loading, on the Lorentz factor, that's a typical information on the density. That's the typical information neutrino can give you. Right now, we didn't find any coincidence, but even without the coincidence, you can put some constraint on the density factor.
But the uncertainties are not too large to say something. The uncertainty is not too large.
That's for depending. Yeah, you have to do it burst by burst mainly. Okay. But for population, you can look. Damien has done a lot of studies on this during his PhD. And you can try to do some tests
to comment something.
Sorry.
I think the most familiar advance in the understanding the physical neutrino is the mass oscillation. That is quite common, and probably that is included in several of our calculations, for instance, to understand supernova. However, there are some other properties that has not been explored, and they are quite feasible if we understand that, for instance, the standard model has limitations to explain mass oscillations, and the simple extension of the standard model can even propose new properties, non-standard properties of neutrino. Just to mention two of them, charge radius and electromagnetic moment, which are not familiar because this is a relatively new discovery. This has to be explored, for instance, to understand better the supernova phenomenon. And well, that is in fact also an announcement for my talk for tomorrow.
Yeah, that's for sure. If you detect a supernova, that's for sure. You have a lot of physics of, but it is more low energy neutrinos, and here you have a lot of physics to understand this standard supernova explosion. And you can find some supernova physics, some nuclear physics, some neutrino particle physics. You have a lot of things if we detect. We know that if we detect, for example, a galactic supernova, now we will not detect 10 to 20 neutrino like in 87. Now it will be around 10,000 to 1 million neutrino. So you see that we have a factor 1,000 to 1 million more event rate. And so we can do some really detailed time variation and stuff like this. So if this happens, we hope soon, to have a galactic supernova. We are waiting it since 40 years now. So it could happen, 3 per century, it could happen soon. We will have huge data, and so, of course, here, optical telescope will be important to characterize the supernova. Even if it's on the galactic plane, it will be difficult to follow up, but here you will have a clear science case.
Other questions, comments? I think if there are no more questions, I propose you to stop now, or say in 2 minutes. You have 2 more minutes to find the question you want to ask. So in that way, we keep energy for the discussion of tomorrow. So nobody, no regrets? Okay, so I propose to finish now. I don't know if the organizers, Alan or Stefan, you have something to say or some announcement, but I consider the session of today, the scientific session, as closed. And see you tomorrow. Damien was asking about the excursion and the social dinner where they are, but it's okay. No, but I don't know. The organizers, do you have something to say before we close everything?
No, rendezvous tomorrow at same time.
Same time tomorrow. Yeah.
Okay. So see you tomorrow, and thank you very much for the presentation and the discussion. Bye bye.
Thank you very much. Bye bye.
Thank you to you.
Bye.